Let us begin. I think it's time. I could be wrong. I think it's time. Yeah, it's time. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for this class. Thank you for your creation and all that we can understand about it. Help us to glorify you what we do this morning and just understand a little bit about the curl and divergence and vector calculus, Lord. In my prayer, Lord Jesus. Amen. All right, so let me prove some things about the divergence and curl here this morning. Now, if you follow my methods, you'll notice I'm probably going to end up solving some of your homework here. If you've already done that homework, my apologies, but I hope you'll now see that there's a better way to do it. So, well, maybe not now, but in a few minutes. So, and I say better way in the sense that the notation I'm going to use is just easier, all right? So, if I have a vector field f, first of all, I'd like to write it as the sum I equals 1 to 3 of f sub I x hat sub I. Right? Now, that's just a fancy notation for f1, f2, f3. Right here, f sub I is a mapping from like R3 to R. All right? That's the component function of the vector field. The component functions of a vector field are functions of the Cartesian variables x1, x2, x3. You know, our typical notation in here has been what? Like x1 is x, x2 is y, x3 is z. It's just super useful to index the Cartesian variables like this for the sake of having like way nicer formulas. So, likewise, we'll have g is equal to, you know, the sum, say, I equals 1 to 3 of gi x hat I. And if writing that is too much in your notes right now, then just write sum. Don't write I equals 1 to 3. Just write sum. Save yourself the I equals 1 to 3. Just let it be understood that your sums are going from 1 to 3. That's an okay notation. Physicists drop the sum altogether and use what's called a repeated index notation. But anyway, in this notation, we have some things that are true. First of all, the dot product of two vector fields we can define, and it's simply the sum over I equals 1 to 3 of f sub I g sub I. That's f1 g1 plus f2 g2 plus f3 g3, written compactly, okay? That's the dot product of the two vector fields. We can also define the cross product of two vector fields. And the super slick formula for that is this. Sum over I j k, epsilon I j k, f sub I g sub j, x hat sub k. So let us keep in mind that this is the formula for the cross product and what follows. That's a nice way to quickly and efficiently write all 6 non-trivial terms in the cross product in a nice unified, I would argue, beautiful notation. Mathematicians tend to disagree with me. They like other things. All right, so then I introduced a couple things last class, right? I introversed, what's that? I don't know, but let's not say it again. The divergence of f, by definition, is the sum I equals 1, 2, 3 of partial f sub I partial x sub I. So it's the sum of the partial derivatives. In effect, it's the dot product of the gradient vector, the nabla vector, and the vector field. Though some people will actually put a vector over the upside down triangle to emphasize its vectorial nature. But then we also have the curl, and the formula for the curl here is it's pretty much the same as the curl of the cross product above, but it's the sum over I, j, and k of epsilon I, j, k partial I f sub j, all of that in the kth position. That's just a fancy way of writing those 6 partial derivatives, suitably antisymmetrized, put in the appropriate components, 1, 2, and 3. The first component of the curl involves second derivative, the derivative of the second and the third components with respect to the first and with respect to the second and third variables, right, and so forth. Okay, so let me start out with something easy. Can we prove the divergence of a constant plus a vector field plus another vector field? How does that work? I don't think I did this last time, but it's been a while. Did I do this last time? No, okay. So here, what would the formula be? Well, by definition, this would be the sum I equals 1 to 3 of, I guess I'll write it in this notation, partial x sub I of CF plus G, the ith component of that, right? Now, what is the ith component of the scalar multiple of a vector plus another one? Remember how we do that? That's like earlier in the course, but not hard. We do partial xi of CFI plus GI. That's the ith component of CF plus G vector. All right. And then we know properties of the partial derivative. Like the partial derivative is linear. The partial derivative allows us to pull constants out. So we use those properties of the partial derivative combined with properties of the finite sum to pull the sum of pull the C out of the finite sum. And then we've got partial f sub I, partial x sub I, plus the sum over I equals 1 to 3 of partial g I, partial xi. But what are we looking at now? Well, let me emphasize what's going on here. What you're looking at is this right here is what? And what's this over here? Yeah, the divergence of f, right? Del dot f. And over here, del dot g. So there you go. That's one of the properties of the divergence. Divergence of the sum is the sum of the divergences, and you can pull a constant out if you want. The neat thing is, almost the same proof verbatim holds for the curl. How would this proof be different if we wanted to prove the corresponding property for the curl? What goes on there? See, if we have the curl of a constant plus another vector, we have the sum, I'll just say over ijk, of epsilon ijk partial x sub I of the ith component of this, which we just talked about, jth component rather, which is cfj plus gj. All of that goes in the k component. So then what do? We use the property of the partial derivative, which is what? We can pull the constant out. We can use linearity, so we've got constant times the sum over ijk of epsilon ijk partial fj partial xi x hat k plus the sum ij and k epsilon ijk partial g j partial xi x hat k. Okay, so what's that? Now this one, if you already did this homework problem without my waves here, it wasn't that bad, right? How many terms are you actually doing? Maybe this wasn't a homework problem though. Oh yeah, the homework problem's not this simple, is it? The homework problem was about a product rule, wasn't it? So if you did problem 92, like the latter part of it, you've got the curl of a product of two functions. That means you're looking at 6 non-trivial derivatives, of which every one is a product rule, which brings you to 12 terms if you just do it in the just straightforward brute force notation, right? If we use this kind of notation, that problem becomes much easier. So what do we have? We've got C times what? This right here is the curl of F. And this guy over here is the curl of G. Now, if I ask you to prove a property of the curl or divergence on the test, do you have to use this notation? No. But should you? Yeah. It would make it way easier, right? Especially if it's something like I'm about to do. How about the curl of a function times a vector field? I'll use G. How's that go? So again, the same formula. We do the sum over ijk, epsilon ijk, that gives me the anti-symmetrized product like I partial xi of f times gj x hat sub k. Now let me emphasize off to the side what I'm doing there. I'm telling you that if we multiply a function times a vector, right? If we multiply a function times a vector, seems like I'm out of red. Now there's one. A function times a vector, how does that work? So like a function times g. I'll do it out explicitly here for a second. So that looks like what? That's fg1, fg2, fg3, if I go back to the brute force notation for a second. So what that all means, of course, is that by definition, the ith component, well, the jth component of this is just f times g sub j. So that's the jth component of the scalar product of the function f with the vector field g. All right? And then, well, then what you do, this, see that right there? That's the partial derivative of a product of a function, two functions, right? F and g sub j. So for a product, we use the product rule. But here, it's the product rule in the sense of the partial differentiation we've been doing all semester long, right? So we've got partial f, partial x sub I times gj, all right? Plus f times partial gj, partial xi, all of that, times my x hat sub k. I'll write down one more step here just to be super explicit. So that is going to give me the sum over I, j, k, epsilon I, j, k, partial f, partial xi, gj, x hat k. Trying to emphasize that the derivative doesn't go on the x hat, it just multiplies it. Plus the sum, I'll get out of the way here in a second, ijk, epsilon ijk, f, partial, I guess I should pull the f out. And pull that f outside of this because it doesn't depend on the index. Pull the f out. Partial ijk, partial gj, partial xi, x hat k. Again, sorry I'm in the way. Okay, so what's going on here? So the question is, do you guys understand what partial f, partial xi is? We need to understand what we're looking at. So I need to remind you something we talked about last time, and we've talked about it before, though. It's not new to yesterday, which was Friday. The weekend doesn't exist, right? Let's see here. So like gradient of f, right, is what? partial f, partial x1, partial f, partial x2, partial f, partial x3 in our current notation, right? In other words, it's equal to the sum over I of partial f, partial xi, x hat sub I. But anyway, my larger point to you is simply this. This right here, right, is what? That's exactly the gradient of f. Yeah? It's the gradient of the scalar function f. It's the ith component of the gradient. See that? So let's interpret what we have. What we have here, what we're looking at, is exactly the curl of the gradient with g plus f times the curl of g. There you go. That is a product rule for the curl. It's also the solution to part B of problem 92, which I guess you guys would be happy about, right? Unless you're a person who's already worked it out in gory brute force detail, in which case you might be less happy about it, in the sense like, I could have done it this way if I'd been lazier, if I procrastinated, right? You're not all engineers, so you don't all value procrastination as deeply as some. But the highest value of the engineer is procrastination. It's one thing to complete a homework. It's another thing to complete a homework hours before it's due, in the absence of sleep. If you can actually finish it, pull it off, and complete the homework, it's one of the greatest states of being as an undergraduate in engineering. Yes. Yeah. You guys shouldn't be agreeing with that. But it's okay. You have a lot of companions in that philosophy. Because whenever I make these comments, they always resonate with all the engineering majors for some reason. Listen, it's okay. So, all right. So you guys tell me what's the other I won't prove everything here. Other elementary so another property that you're going to prove is like the divergence of a function times a vector. That works out to, if I remember right, the gradient of f dotted with g plus, oh man, goodness. Oh, it's got to be the function times the divergence. That's the other, so you're proving that is the other part of your first homework problem, okay? And you can do it in brute force notation if you want, but I would encourage you to try to do that proof in the notation of like the first calculation I did, like this notation over here, right? How would it start? I won't finish it, but how would it start? This would start with, that's equal to the sum, I equals 1 to 3, of partial xi of, what's the ith component of f times g? Well, it's f times gi. If I write anything more, I'm going to solve it practically, okay? So I'll stop there, but you apply the product rule, and then you break it into two sums, one of which you'll identify as the dot product of the gradient times the vector. The other one is f times the divergence of the vector field. Okay, great. Now, there's more, though. There's more. So there's these elementary properties of the curl and the divergence, and they're nice, but there are deeper truths. So here's the harder, non-trivial, let's say. Not that any of these are trivial, but these are very more non-trivial props of the gradient, and here they are, and I have to look at my notes for this. If I just try to rattle these off without consulting my notes, I'll be wrong. But here's how it goes. If you have the divergence of a curl, well, the divergence of a curl, it turns out, is equal to g dot the curl of f minus, that's a surprise, f dot the curl of g. And number 2, the gradient of a dot product of two vector fields. It turns out, whoa, oh goodness gracious, it's the curl of the, it's the cross product of the curl of f with g plus the cross product of g with the curl of f, yowzers, plus, look at this one, f dot del acting on g plus g dot del acting on f. Yep. And then 3, and I think this should be curl. There's a typo in my notes right here. So the curl of a cross product, you're like, who would do that? You know? Who would take the curl of a cross product? What monster, right? We would. So this is g dot del acting on f minus f dot del acting on g plus f multiplying the divergence of g minus g multiplying the divergence of f. Hoi. The first one of those I can prove fairly easily. All right. The first one ain't that bad. Yeah.
What does it mean for f dot del?
Ah. So you're wondering what in tarnation I mean by this expression, right? So this literally means the sum I of fi partial xi acting on g. So this is a vector. So literally that's equal to the sum over I and j of f sub I partial g partial x sub j, I believe, partial x sub I, x hat sub j. To be more explicit, it's literally like f1 partial 1 plus f2 partial 2 plus f3 partial 3. That acting on g1, the same acting on g2, the same acting on g3. You guys can't see that, I'm sorry. I chose the wrong color for beyond the event horizon. Like you'd have had a chance with black, but with red, there ain't no way you're seeing that. Sorry about that. Now, I think if you search the posted solutions, I do think I actually have a proof of either 2 or 3 in the notes. I can't remember. The proof of 1 is in the notes as it stands. That's pretty simple. In the notation we're currently using, that's not too bad. I could prove 1 in here. But I'd actually, if you don't mind, I'm going to skip the proofs of any more of these. I think I've done enough of these kinds of proofs for your class, if that's okay. I'd like to apply them. So here's an example that you might think is interesting, and well, you might not. I think it's interesting. Oh, rats! I've forgotten. So sorry, guys. I turned the page and realized I'm a dummy. So I need to do a little bit more here. Further props. So, second derivative identities. These are actually even more important than the ones above. So first of all, the divergence of a curl is 0. Number 2, the curl of a gradient is 0. And number 3, the curl of a curl, it's not 0, but it's something. And the something that it is the gradient of the divergence minus what's called the Laplacian, nabla squared of f. Now here, this nabla squared of f, nabla squared is literally partial x sub I squared, rather 1 plus partial x sub 2 squared, partial x sub 3 squared. Again, my apologies. Now those I can prove. Those it might be worth. So you guys pick one. Pick which one you want me to prove, not including 3. So would you guys want to see the proof of 1 or 2 there of the second derivative identities? That'd actually be worth our time. 2. 2 it is. What's 2 say? Oh, triangle cross triangle f, right? So the curl of the gradient is 0. So let me write that out. This is the sum I, j, k, epsilon I, j, k. And here we go, partial I of partial f, partial xj, all acting on x hat sub k. Or if you like, we could write this middle term as what? Partial squared f, partial xi, partial xj. But the key is that's equal to what? We know that the derivatives do what? They commute, right? So we could swap that out for partial squared f, partial xj, partial xi, right? And so this, of course, is equal to the sum over I, j, k, epsilon I, j, k of partial j, partial f, partial xi, x hat k. But then what I do is I'm going to erase this and put a minus here and put epsilon j I k. See, that's one of the main properties of this anti-symmetric symbol, is that whenever you switch a pair of indices, you get a minus. So like epsilon ijk is equal to minus epsilon jik. Like 1, 2, if you switch it to 2, 1 gives you a minus. 2, 3 switch to 3, 2 gives you a minus. 1, 3 switch to 3, 1 gives you a minus. All right? And so then what am I looking at? Well, I've got the j index matching up, the I index matching up, and k. So this is exactly minus the curl of the gradient of f. Aha! It's what then? Right. If you can show something is equal to minus itself, this implies that the curl of the gradient is 0. Right? And the proof of like 2 is similar. The proof of 3 rests on a non-trivial identity, which I might have in my notes. I don't remember. If it's not in my notes, it's definitely like, I definitely have a proof of it written somewhere in public display. But, oh yeah, it's on page 332 in all of its glory. I'll show you in a second with the projector. But I want to apply this. So finally an example. I haven't called anything I've done up to this point an example because, well, they're all proofs. They're really just proofs of the proposition, right? So I don't know, I don't call them examples. They're examples of proofs, right? But anyway, and these kind of proofs they're really more in line of like derivations, right? They're not a kind of proof, like the proof of Rolle's theorem, for example. How would you prove Rolle's theorem? That actually requires ingenuity. These proofs just require access to the formulas I started class with. Once you have those and you know the product rule, you can do all these. It's just notation. It's just notation. Proof of Rolle's theorem, that requires genuine creativity. Now here, I'm going to share with you some things. These are called Maxwell's equations. So the divergence of the electric field is 0. The curl of the electric field is minus the time derivative of the magnetic field. The divergence of the magnetic field is 0. And the curl of the magnetic field is equal to mu naught epsilon naught partial derivative of the electric field with respect to time. So these 4 equations that I've just written down for you, they capture the theoretical core of what's called electromagnetics. We've known this stuff since about 1860 or so, although not in this notation. When Maxwell wrote these equations down first, he was writing them as 20 separate partial differential equations. And there was some stuff about constitutive relations and things were in there that was more complicated. But anyway, by the turn of the 20th century, this is how we were looking at them. Now, these are Maxwell's equations in vacuum. So in the absence of like charge or current, this is what Maxwell's equations look like, okay? So if we know the identity that we found in the proposition over there, we can play games with Maxwell's equations and see what happens, right? Like, I can do what? I can use property 3 over here. I can take the curl of the curl and see what happens. What happens when I take the curl of the curl of the electric field? What do I got? So you guys try it out. What happens when we take the curl? Well, should I use the electric field or magnetic field? I don't know. I guess I said electric field, so I'll stick with it. What's the curl of the electric field? What's that equal to? Well, apparently, it's equal to the curl of minus partial b partial t, right? On the one hand, I'm just plugging in trying to remember which law that is. Oh man, this is why I need to teach physics too again. I'm forgetting the names of things. I can't remember if that one's Faraday's law or if it's the Ampere's law. I think this one is Ampere's law with Maxwell's correction. That means this must be Faraday's law. But anyway, if we can commute the time derivative, right? In other words, I'm assuming that you can commute the partial derivatives with respect to time and space. If we can do that, then we've got the time derivative of the curl of b with a minus, right? But what's the curl of b? Well, the curl of b, you see right above, it's mu naught epsilon naught partial e partial t, right? So what you got? You've got a minus mu naught epsilon naught partial squared e partial t squared. That's what that is. But on the other side, so that's just using 2 of Maxwell's equations, all right? But on the other side, if I use the identity, what do I have? I've got the divergence, the gradient of the divergence of f, right? So I've got the gradient of the divergence of the electric field. And then what's the other term? Minus the Laplacian squared of the electric field, right? But what is the divergence of the electric field? Well, it's given to be 0 here, right? So this is 0. So what's this all tell us? This tells us altogether that the Laplacian of the electric field is equal to mu naught epsilon naught partial squared E partial t squared. Now that might not look much like much to you, but when you study mechanics, like if you take Professor Dromby's class, for example, not mine, but Professor Dromby's class, she typically spends a couple days on wave motion. My class just goes a different direction, so we don't tend to cover it, but if you were to take differential equations with me, then I would cover wave equations there. But anyway, this is a wave equation. So like what this looks like is second partial derivatives in space are equal to a constant times second partial derivatives in time. That is actually the equation of a wave. And if you study waves, you'll find out that the meaning of this coefficient is the speed of the wave. All right? Well, it's not quite that, actually. This tells us that the speed of the wave is 1 over the square root of that. Now, 1 over the square root of mu naught epsilon naught is approximately equal to 3 times 10 to the 8th meters per second. Does anyone know what that is? It's the speed of light. That's right. So once you write down Maxwell's equations, and you know vector calculus, you can derive that the electric field, and by the way, the same thing happens for the magnetic field. The magnetic field also satisfies the same wave equation. So you'll find out that the electric and the magnetic fields both satisfy a wave equation, and the speed of the wave is equal to 1 over the square root of mu naught epsilon naught. What are mu naught and epsilon naught? Well, these are respectively the permeability and permittivity of free space. So, in other words, we're saying the speed of light is just a property of space and time itself. That is a mathematical consequence of Maxwell's equations. See, at the dawn of the 20th century, physics as we knew it, there was classical mechanics, like Newton's classical mechanics, which have been around since like the 1660s, refined by the work of like great French theoretical physicists, Italian, and all kinds of theoretical physicists in Europe over the past 100 years. They were incredibly successful in describing the motion of planets, right down to a few just small missing things, like the perihelion Mercury, just a few little hanging chads, if you will, of celestial mechanics, mostly able to explain the motion of the planets by just solving like Newton's laws and adding correction terms. So there was like incredible experimental evidence for Newtonian mechanics being really, really right. Like we spent the better part of a century, hundreds of mathematicians working on approximating things, show planetary motion followed from Newton's laws. But at the same time, there was this new punk theory, electromagnetism, about 50 years old, maybe not even that, right? And in it, a mathematical consequence of it is that the speed of light is independent of where it's coming from. It's a property of space and time itself. So in fact, as you study these things more deeply, you'll learn that Maxwell's equations they're intrinsically relativistic. They're already what's said to be covariant with Einstein's special relativity. So once Maxwell wrote these equations down, it was just a matter of time until somebody came along and discovered relativity. It happened to be Einstein, but it could have been anybody. It had to happen. It was a mathematical necessity once we found electromagnetism. Anyway, so personally I think it's interesting. Now, you don't have to disagree, you don't have to agree with me, but one of the main reasons we're studying vector calculus is to understand electric and magnetic fields, how to calculate their flux through surfaces, and also to calculate their circulation along curves, right? So that's where we're going. Do you guys have any questions? I can do more examples. Should we do that? Yes, no, maybe so? I think we have a quiz tomorrow. What's it on? The quiz is on curl, divergence, and gradient, right? So what would be a likely quiz question?
Find the curl.
Find the curl and the divergence. That seems right, right? So like possible problem, something like this. How about f equals to x squared plus z, y cubed minus x, z to the fourth plus xy. Calculate the curl and divergence. Like that could be that might be the quiz, right? Can you do it? I'll do the divergence. The divergence is 2x plus 3y squared plus 4z cubed. Done. Now the curl, well, the curl I have to think about, admittedly. All right, I can't hide that. I mean, the curl's pain. It's the same pain as the cross product, so I'll write it down symbolically here. So we've got partial, oh rats, oh fine. Let me take my medicine. Determinant, x hat, y hat, z hat, partial x, partial y, partial z, and x squared plus z, y cubed minus x, z to the fourth plus xy. All right. So what we got here? We've got ourselves an x hat times partial y of z to the fourth plus xy minus partial z of y cubed minus x minus y hat partial x of z to the fourth plus xy minus partial z of x squared plus z, close parenthesis, plus z hat, yowzers, partial x of y cubed minus x. You notice there's a pattern? Do you notice that the things that contribute non-trivially to the divergence are exactly the things that don't matter to the curl? There's a pattern there, isn't there? Know what I'm talking about? Let me just point it out to you with my handy dandy marker here. The terms which contributed non-trivially to the divergence were this, this, and that. That gave me that, that, and that, right? Agree? You will agree. No? All right, fine. Don't agree if you don't want to. This guy, where did that go to? That appeared here. And where else? Here, right? Both of those give non-trivial derivatives. And both of those, well, that term was irrelevant to the divergence, right? There's kind of like a mirroring of what matters to the divergence versus the curl, isn't there? But anyway, let's calculate what we got. Looks like we've got an x, comma, minus y. Oh, there's plus 1, right? From this guy. Minus minus give me plus. And that gives me a minus 1. And that's it. So there you go. That's the curl, right? The other stupid game I could play on the quiz that wouldn't take a lot of time would be to like give you a curl, give you a divergence, and then like multiply it by a function and ask you to calculate symbolically. Basically to use the properties that we proved today to do a problem. We could do that. You look confused. So suppose I told you like the curl of g is equal to 3x squared y z. and I'd say f is equal to z cubed, calculate, the divergence of f times the curl of g. I mean, this is a stupid problem, but you could do that, right? Stuff like that. Not that that's interesting. Here's a more interesting question. Could that be a curl? Is there anything special about a curl? How can you test whether or not something's a curl? Is this even reasonable? Is this legit? Or must it quit? Well, look at this property over here. The divergence of a curl is 0. Is the divergence of that 0? What's the divergence of that? 6x, right? The derivative of 3x squared with respect to x is 6x. The derivative of y is, with respect to y, is 1. Derivative of z with respect to z is 1. Ooh, it is definitely not legit, right? So that's an impossibility because of the second derivative identities. Okay?
Could you have,
So the quiz tomorrow is open notes, so I don't want to force you guys to like write all the identities on the note card or something. That's not what I'm after at the moment. You can have your notes open to look at these, okay? Yeah.
could you have constraints on it to make a curl, for instance, x is minus 1
Well,
stuff like that?
that's a harder question to answer. Like how exactly do you characterize vector fields which are curls? I think that's one of the deeper goals of my chapter that really is only maybe completely answered towards the end. And I'm not sure it really ever is entirely. I can tell you when it's not. And we can also play the game of like, here's a vector. Can we find a vector who is its curl, right? Another game we can play, an interesting game, perhaps a dangerous game, is if I have, A, B, C, can I get that to be equal to like x, 1, 3? Can I find functions A, B, and C whose curl is that? Well, I can tell you this much. If you look at the divergence of that, you get what? You get 1. So the answer is no. So to make it interesting, I better make sure I put something here that's divergentless. All right, let me hit stop on the record.